Hi, today I'm going to be going over the one-wire circuit on an older MacBook Pro because on these machines it's a little bit more confusing than what it was on the newer MacBook Pros. Now this is something that I wanted to do in real time. It's been something that's been getting asked a lot and I wanted to go over it in a repair video today, and some of my repair videos lately have kind of been going like shit, and this one really took the cake. Like, I say that I post everything I post even when I screw up, and this repair actually worked. Everything came out well, but there's kind of a limit to how dumb I'll allow myself to look on camera, and today I definitely managed to reach that limit with this video. So I'm not going to be doing this in real time, but I am going to walk you through it, and it's going to be after the fact, so it's going to be a little lame compared to one that's done in real time, but hopefully it winds up being something that's somewhat informative that you can use and kind of learn something from. So I'm going to open up a schematic for one of the newer model machines here, because with the newer model machines, it's a little bit easier to understand how the one-wire circuit works compared to the older one. So once you understand the newer one, understanding the older one will become a little easier. But if you don't understand the newer one or the older one, then it's going to be a little bit confusing all around. So that said, let's get over to discussing that part of it. So let's move over to the screen capture here. So we're going to go over to the screen capture here. Is that screen capture? Are we in screen capture? Oh, this is not screen capture. We're getting close. Oh, capturing the wrong fucking screen. There we go. And now I just gotta shrink me. No need for me to be big. Yeah, go away, asshole. Go down here. There we go. Fine, go away. Alright, so, that being said... Hi, kitty. Good kitty. All right, so we're going to go over to the one-wire circuit. So this is pretty simple. The whole idea here is that the one-wire circuit is going to allow the adapter, see here where it says MagSafe DC jack, it's going to allow the adapter to talk to the SMC. So the adapter has 18 volts, DC electricity, duh. It has ground, again, duh, required for a circuit. But the one that confuses people is adapter sense. Adapter sense the adapter, turn on. So that is going to go over to this IC. This IC over here has ext and int. Now, let's think about this here. Ext as an external, as in the charger, and then int as an internal, meaning, man, newer versions of Open Broadcaster have this slow mouse shit on both of my computers. I'm telling you, when you find good software, and it's not software that connects to the internet or can have security vulnerabilities, don't fucking update it. Just never update it. Anyway, so we have sys one wire is going to be internal. This is going to be for the SMC. Ow, thank you for making me deaf. So the SMC here, see, sys one wire, it says bi for bidirectional data line. That is the SMC over here. It's going to say in the bottom right corner of the schematic here. See, it says SMC. So this IC is going to allow the SMC to talk to the charger, and that's how you get your green light on your MagSafe charger. Now, this IC has another pin, VCC. VCC, VDD, VIN are pretty much the same shit when it comes to these schematics. It's just the power pin that's required to turn it on. So, like this shitty little interface that I have. It has a cable going into it. You can think of this cable as the VCC pin. If I don't plug that in, it doesn't get power. So this chip over here has a VCC pin. That's where you apply 3.42 volts when you want it to turn on. Now, its 3.42 volts is going to come from this IC over here. This is a logic gate. This logic gate is going to take PP3V42, which is 3.42 volts, and it's going to pass it on to this chip, which is going to allow the charger to talk to the SMC. It's going to do that if SMC BC ACOK is present. So let's find SMC BC ACOK in the schematic. Now this over here, again, this is where a little bit of common sense is required. In charger ACOK, little equal sign hamburger looking thing, and then SMC BC ACOK. So what this is telling me is that for the rest of the schematic, charger ACOK is going to be used instead of SMC BC ACOK. And that's fine. Now, this is U7000. This is what's going to take charger voltage. This is a buck converter. If you don't know what a buck converter is, watch the buck converter videos. This is going to take the 16 or 18 volts from the charger and turn it into 12.6 volts for the machine. Now, this chip is what's going to shoot out charger ACOK. Now, it's not going to shoot out charger ACOK unless it gets 4 volts on the charger ACN pin, right? So make sure you're following here. So you have from adapter, that's the 16 or 18 volts from your charger. It's going to come through here. And then this voltage divider, if you don't know what a voltage divider is, check my videos on what a voltage divider is going to take this voltage divider of R7010 and R7011 are going to take the 16 volts. It's going to take the 16 volts from the charger, and it's going to turn that 16 volts from the charger into 4 volts for the charger ACN pin. Now, once it gets 4 volts in the charger ACN pin, if the chip itself is not fucked, and it is also getting power on the charger DCN pin, check R7005, because in the case of a knockoff charger, it's always going to be blown, then it won't shoot out charger ACOK. But if it's getting its 16 or 18 volts on charger DCN, if it's getting its 4 volts on charger ACN, it will shoot out charger ACOK, which is SMC, BC, ACOK. I can barely type today. Here we go. Which will allow this logic gate to pass 3.42 volts onto this chip. Once this chip gets its 3.42 volts, it allows the adapter, again, this is the charging port over here. It allows the adapter, this adapter sense line, to talk to the SMC. That's the newer one-wire circuit. Simple, easy, breezy, beautiful cover girl. I have that stuck in my head. I don't know why. I remember watching cartoons as a kid, and there was a commercial, and it would go, easy, breezy, beautiful cover girl. I haven't heard that shit since like 1999. And today, just in the middle of nowhere, like 4:30 in the middle of the day, I just hear that shit in my head like 5 times. It's driving me fucking crazy. Anyway, that's probably why none of my videos went right today. So let's go over to an older one-wire circuit. Now, the reason I bring this up, I know people are going to say, why the fuck should we care about this? This is from 2009. Firstly, this is for a 17-inch MacBook Pro. Now, a lot of people like the 17-inch MacBook Pro. They don't want to move on, so they don't want to try something new. They want to stick with what works, and they like this device for whatever reason, so they're not buying a new one. So there is some value in fixing these. And the second thing I want you to understand is that a lot of people who watch these videos are not from the United States. In the United States, your $1,000 device dies, you buy a $1,500 one next week. In other countries, people, you spend $2,000 on this thing. You expect it to last for the next 10 or 15 years. It's just the way it is. So a lot of people will still bring these. So I want to talk a little bit about how this circuit works, and I want to bring up some of the flaws in how Apple drew the schematic, because I think a lot of the misunderstanding of this circuit is not necessarily from the fact that it's more complicated. It's rather from the fact that the way Apple draws the schematic is fundamentally fucked up and confusing to a lot of people. So let's go over that. So everything else in this circuit is the same. So when it comes to charger AC in, charger ACN over here, am I still in? Yeah, I'm still in Sumatra. Charger ACN, you still have the voltage divider here. U7000 is still going to shoot out charger ACOK. All that stuff is still true. That stuff is still the same. But it's when you get to the SMC, BC, ACOK area that you really get to the confusing part. So let's, yeah. So this is a mouthful for most people. This is a bit of a clusterfuck. So let's go over it. Now, let's break it down. Adapter sense, right? Same adapter sense line over here. You have your adapter sense line. Your adapter sense line is going over to this transistor and then this other transistor, which is going to allow it to talk to the SMC, right? Now, remember that this is a data line. And like all data lines that are made this way, it's going to have to be pulled up by a pull-up resistor. If you don't understand how that works, check out my video on how a pull-up resistor creates a data line. Take a look over here. See this over here? This is the newer one-wire circuit. Even after this chip allows the external adapter sense to talk to the internal, which is the SMC, you still have this resistor over here, this pull-up resistor, between the 3.42 volts at the VCC pin and this one wire so that there can actually be a data line. Now, take a look over here at this one-wire circuit. Let's check it out. Let's check out what goes on here. So SMC, BC, ACLK comes through this resistor, and it's going to, now this over here is an N-channel Mosfet. So this is going to allow the power to flow between source and drain if the voltage in the gate is considerably greater than the voltage in the source. Now, if we look at the voltage on the source over here, you're going to notice, if I actually get my fucking head out of the way, you'll see that the source is going to ground. Ground is 0 volts, which means that if I put virtually anything on the gate, this is going to open and it's going to allow power through. So if SMC, BC, ACOK is present, if U7000 says everything's good, then at that point, this will allow whatever's on the other end, whatever on the drain, to go to ground. Now I want you to take a look up here. This over here is a P-channel MOSFET. By the way, if you don't know how to tell if it's an N or a P-channel, or you don't know what they do, you can watch my videos on transistors, and you can also check and just Google this little number here and it'll tell you. This up here is a P-channel MOSFET. This works a little bit differently. The N-channel MOSFET is going to let the power through when the voltage on the gate is higher than the source. The P-channel MOSFET is going to let it's going to let everything through. The resistance is going to go down when the voltage on the gate is considerably lower than what's on the source. So let's look at it like this. Let me just make it simple by minimizing what it is you see on the screen. Here we go. Okay, so we have 18 volts up here. 18 volts up here going on the source of the transistor. And then we have a resistor, R6911, which is going to take that 18 volts that's on the source and it's going to place it on the gate. Now, knowing that with a P-channel that the voltage on the gate has to be lower than the voltage on the source in order for it to open, what R6911 is doing is it's pretty much ensuring that this transistor is constantly in a mode of high resistance. It's not letting power through, right? So let's check out over here. Now, what R6912 does is it then turns this into a voltage divider. Stop fucking with the recycling. Clinton? Sometimes you gotta put your foot down. Over here, this is pretty much taking the 18 volts from the source and putting it on the gate. With a P-channel MOSFET, the source voltage equals the gate voltage. With this particular MOSFET, it's going to be in a high impedance mode. It's not going to let power through. Now, what we do over here with R6912, now this is a voltage divider. It's not just one resistor. With this resistor over here, if we give this resistor R6912 a path to ground, it then becomes a voltage divider. So rather than 18 volts being put from the source to the gate, now the 18 volts is going from the source to the gate, but then R6912, if we give it a path to ground, will then lower this to maybe 9 volts or 7 volts or 11 volts or something like that. I don't remember the exact voltage. It's not like I work on relics and antiques every day, but every now and then I do. So if this opens, if this transistor is allowed to open, then it will make this into a voltage divider. If R6912 gets a path to ground and turns this into a voltage divider, then the voltage on the gate here is going to be lower than the voltage in the source. If the voltage in the gate is lower than the voltage on the source, then this entire circuit will open, which will allow 18 volts through here. Now let's take a look at what happens when you allow 18 volts through here. Stop fucking with my recycling can, kitty. Oh. Let's see. I know, cat. I know, Clinton. You're a mad kitty. It's okay. Okay, what type of transistor are you? You are an N channel. I know, you could have told me that, right, Mr. Clinton? So. Oh, my other monitor froze. Boo. Oh well. That's what happens when you use a dead video card in your recording computer. So, this is going to open when the voltage on the gate is higher than the voltage that's on either the source or the drain. I forget, my brain is fried. Anyway, 18 volts is going to be higher than what's on any of that, so it's going to allow these to open. So, you need the voltage to go from the source to the drain here in order for this stuff to open, and you also need that for the rest of what's going on here to work. So let's take a look at what's going on over here. And let's also take a look at what makes this system so confusing. Now, a couple of the things that make the system confusing is the fact that Apple has completely fucking failed, and I mean completely fucking failed, at making any of this make any sense. So, how's it going, little kitten? So, if we go over here to the board view, first things first is where the hell is R6918's pin 2 going to? Where is this line going? I see pin 2, I don't see it going anywhere. Let's see, R6918 on the board view, and then we're going to check out pin 2 and see where that's going. So pin 1 is one wire in, and pin 2 is ground. Okay, so pin 2 over here is going to be ground. Now, second thing to get here is on Q6915. Where is pin 4 going? I see the drain of this is one wire enable. Where's the source? Let's take a look at Q6915, pin 4. Pin 4 is also ground. Okay, this is making some sense now. So the voltage on the gate over here, you're probably not going to want that to be 18 volts. Because that's pretty much going to say, okay, even if adapter sense is fucked, send 18, because let's say the DC inboard dies, right? Adapter sense should be like 3.5 volts. If the DC inboard is fucked or something is fucked with the system, adapter sense can go up to 16. You don't want 16 volts going to the SMC on this one wire. That's very, very bad. That will kill the SMC. So this will pretty much not allow the adapter sense line through if it goes over a certain voltage. And so this is a voltage divider over here that's probably going to lower it to something like maybe 7, 8, something around there for the gate. But also, this over here attaches to ground. Now, the reason that I think this confuses a lot of people is it's not even because they don't understand how the circuit works. It's that they don't know where the individual elements are even fucking going because they never bothered to fucking draw it. So look at Q6915. Let's take this in a context again, right? So the way that this entire general system is going to work is that this over here is going to allow the cis one wire line to go from the adapter sense to the SMC. So we need to get these transistors, or these Mosfets, I guess. A Mosfet is a transistor, but a lot of people have been trolling me lately at me calling a Mosfet a transistor, even though it's a type of transistor. These transistors, to piss off the engineers that watch, we need to get these turning on. And we get these turning on when we have power going through down here. Now, check it out. So we have one wire enable over here. This one wire enable voltage is pretty much going to be the voltage that comes through from this. So when SMC BCAC OK allows this voltage divider to work, when this transistor takes this voltage divider and allows it to go to ground, it's then going to allow this transistor to send 18 volts through. Once this transistor has sent 18 volts through, we now have this voltage divider working because there's power on the other side, which is going to allow these transistors to open and allow cis1 wire to talk to my SMC. However, big fucking however here, where can this all go wrong? Well, this voltage here, one wire enable, meaning enable my one wire circuit, meaning allow these transistors to open, this can all be shorted to ground by Q6915. Now, let's see, this is also an N-channel MOSFET, meaning that if the power on the gate is higher than the power on the source, it's going to send my one-wire enable signal to ground. And the reason that you wouldn't tell that from this stupid fucking diagram is that the lazy piece of shit at Apple in 2009 didn't even manage to draw a line to fucking ground. How much work would that have taken for your $400 billion company? Anyway, but let's take a look at this. Now, this transistor over here is going to turn on and send my one wire enable voltage here, which is the voltage that I need in order for these transistors to work. It's going to send it to ground if one wire overvolt goes high. Now, what's going to enable one wire overvolt to go high? This IC, this one, if it detects something that it doesn't like. So this IC is hooked up to the adapter sense line, and it's also hooked up to the 18 volts from the charger over here, right? See? Makes sense? So, here's what usually happens. Let's go over what usually happens with these circuits. usually what's going to happen is that this over here, see this resistor R6911, where it says 470 kiloohms, it's going to measure 200 or 300 or 100 ohms. Now, I want you to think about the video that I did on resistors and how resistors fail. Resistors usually fail by becoming a higher resistance than the resistance that it's specified to. So a 2 ohm resistor may become a 100 kilo ohm resistor, a 100 kilo ohm resistor may become a 5 million ohm resistor, a 5 million ohm resistor may become an infinity ohms resistor. That's the way resistors usually fail. Resistors don't fail, at least in my lifetime, I've never seen a resistor fail of any type by going down in resistance. I'm not saying it's impossible, I'm saying it's something that I've never seen in like the 10, 11 years of professionally repairing electronics at component level. So, this is probably not going to fail. R6911 is probably not going to fail. So what else could possibly fail to create 0 ohms of resistance between pins 1 and 2? Well, what else is connected? Pin 1 of the resistor is attached to pin 1 of this transistor. Pin 2 of this resistor is attached to pin 2 of this transistor. If the transistor fails internally and this transistor has a short between pins 1 and 2, then you're going to measure a short on pins 1 and 2 of the resistor. So the resistor usually is not bad. What's bad is Q6910. And Q6910 being bad is then going to not allow this entire system to work right when this is shorted. So you replace Q6910, but nothing is working. Now, one of the things you could do at this point as a cheat, not saying you give it back to the fucking customer this way. I'm not saying you give it back to the customer this way. One thing you can do as a cheat, once you replace Q6910, is you can remove Q6915 and U6915. What this is going to do is ensure that voltage is going to the one-wire circuit all the time. You're going to remove Q6915 and U6915s having a path to ground to screw up your circuit. So adapter sense is going to go over here. The voltage from here, this little voltage divider, R6917, R6918, is going to ensure that once Q6910 opens, that voltage goes over to the gate of these transistors, which then allows this one wire to talk to the SMC. I'm not saying that you give it back to the customer that way. I'm just saying that if you've already measured your adapter sense line, and your adapter sense line is 3 to 3.4 volts and not 16 volts, meaning your adapter sense line is within a range that's not going to blow up your SMC, that you can remove Q6915 and U6915 and see if you get a green light temporarily. If you get a green light temporarily, then you can buy a new Q6915 and a new U6915. And it's going to be a pain in the ass because if you're like me and you only stock donor boards that are relevant to your time, you're probably not going to have a lot of LM397s in your parts bin. So you'll have to order it. Regardless of how much the customer bitches and screams, you're not going to leave U6915 and Q6915 off the board. You're not going to let the one-wire protection not be on the board, and you're not going to allow the customer's balls to explode if they plug in a knockoff charger. Don't do that. But it is something you can do because, again, look at this. Q6915. This is where your one-wire voltage over here, remember, this is the pull-up, this is not the pull-up. This is the resistor that's going to allow these transistors to open, that's going to allow your adapter sense to talk to the SMC. That's what you need for a green light. If this transistor is bad or this IC is bad, it's going to tell this transistor to do things that it shouldn't. Or even if the IC isn't bad but the transistor is bad, it may short to ground and it will take your one-wire voltage away to ground. So if you remove Q6915 and U6915, you've then removed your path to ground, which means that you have a one-wire circuit. You have a one-wire circuit, which is literally at this point one wire, which is bad, that is always working. And if you get a green light, then you can invest in buying this and this and waiting. But it's a quick way to cheat and see if your SMC is dead as well and see if it's kind of even worth bothering to fix. It's a way you can cheat and look ahead. And that's the way the one-wire circuit works on this machine. So long story short, as confusing as this entire shit looks, if you break it down, it's very similar to the old machines. And if you ever do get to a point in the schematic where you don't know where something is going, where the Apple engineer was on crack and you get one of these lines that doesn't go anywhere, just go over to your board view software, search for the component, click on the leg that you don't know where the fuck it goes, and on the bottom left you'll get it'll tell you where it goes and it'll give you a little bit of an idea. So hopefully this has been helpful. I know I haven't done a great job at explaining it. I'm sorry for that. I did want to do a real video of fixing this in real time. Again, some of my videos lately have been coming out kind of forgetful and shitty, and this one was just like a new level of forgetful and shitty, and my explanation right now is kind of a good level of forgetful and shitty, but I did want to do a video on this, and it's not something that I come across very often, so I know it's something that if I don't make the time now to do a video on, I probably never will. But hopefully if you're working on one of these older machines with the shitty one-wire, the shitty, huge, complicated one-wire circuit, this helps. And you can see, even if you go to this, like the schematics really do get worse and worse. Like, check this one out. Same one-wire circuit, by the way, same shit. This is pretty much the exact same thing. It's on the 15-inch board from that year rather than the 17. So I just show you the one for the 17-inch board. Now on the one for the 15-inch board, look, they show you these resistors go to ground, right? Look at how fucking nice they were. They put grounds, and the resistor over here goes to this line goes to ground. They were so nice. But look, Q6920, cis one-wire, cis one-wire bilateral, whatever. Oh, pin 3. Where the fuck does pin 3 come from? Where the fuck does pin 3 go to? Who the hell knows? Again, a big reason that people are confused is because Apple doesn't draw this shit. Look, Pee Wee Herman is back Pee Wee Herman has been rehired as the artist that draws the Apple schematics. Look at this. Check it out. So adapter sense goes from... This is such a new level of stupid, I don't even know what to say. So it looks like signal is going to ground, but it stops here. Signal stops here. See, in the good schematic, you have pin 5 is signal, which goes over to adapter sense, which goes over here. In the bullshit schematic, you have signal goes, huh? And then you have adapter sense, and adapter sense just goes in a square and touches itself. It just touches itself. These schematics are such fucking bullshit. I'm telling you, every Apple engineer from 2008 and 2009 must have been on some amazing fucking drugs. I'm incredibly jealous. And that's it for today. And as always, I hope you learned something. If you did learn something, I want to see you apply it, apply this stuff, fix boards, and I will be very happy. And remember, every time you fix one of these boards that would have been thrown away, or you're keeping somebody from buying a new one, and every time you keep somebody from buying a new one, you're keeping Apple from making money. And that's going to put a big smile on all of our faces. That's it for today.